The key to using a formula is to understand the formula as opposed to merely memorizing it. Here's an equation: G is equal to CH raised to the m power, where C and M are numbers and G and H are variables. Actually, this equation is a well-known mathematical formula, but I've kind of hidden the variables and hidden the particular constants. To unravel the formula, I will give you the value of the constant C. It actually was supposed to be pi. With that one piece of information, you might be guessing that this formula has to do with a circle. Given that the variable G really does not stand for gorilla, instead it was supposed to be an A, take a minute to think about this formula and guess what it is. If you guess that the formula is for the area of a circle, you are correct. However, our friend the gorilla looks like he just does not believe that yet. Now let's take a look at one of the formulas from Unit 1. By looking at it, we might even be able to guess some of what these pieces mean. V, well, geez, that probably would be volume. Oh, there's my pi r squared again. That reminds me of a circle, and an area of a circle specifically. Dx, I don't know, that's just a symbol we put at the end, isn't it? Well, maybe it's not. The A and a B would designate a region from x equals A to x equals B, but now let's take a look at what it really does mean. First, let's review the method for finding area under a curve. Recall that the building blocks for finding area under a curve are rectangles. We start by drawing rectangles under or over the curve that will estimate the actual area. The length of any particular rectangle is determined by the height of the function. The width is a small portion of the x-axis designated as delta x. If we build an infinite number of rectangles, delta x approaches 0 and becomes dx in the integral. As we build more and more rectangles, the estimation for the actual area gets more and more accurate. Then by using the limit process, we arrive at the definition of the definite integral. Here is a diagram showing just one representative rectangle that illustrates area under a part of the curve. I would like for you to imagine the top of the rectangle rotating out from the screen towards you. After one complete revolution, what would the resulting 3D object look like? Did you visualize this 3D object? We will be calling this object a disk. An example of a disk is a coin. Any coin is circular in nature, but in addition to that, it has a thickness. Consequently, the coin has a very small amount of volume. Notice that the radius of the disk is a function height, just as it was for area. However, dx now represents the thickness of the disk formed by the revolving rectangle. Let's just take one more look at how that rectangle forms that disk with this animation. Gives you a really good idea of how that rectangle spins around and becomes a coin or a disk. And now let's take a look at if we were to build several disks. Notice they're kind of stacking up sideways there, and they're all pretty uniformly sized, but they're forming and packing in those disks from left to right to then mimic the curve that we have there. You notice there's some overshoot, and so it's a little bit bigger than what's underneath that curve, but it's getting a pretty good representative of what our three-dimensional object looks like. Now let's take a look at that formula from Unit 1. We were correct about V. V is volume, and we had a good idea that pi r squared represented circles, and specifically area of a circle. And then at first we thought, and many students think, that dx means very little if anything, but we found out that dx represented thickness. And then we get a volume because we have pi r squared times thickness, which gives us what we then called a disk. In summary, the formula V is equal to pi r squared dx is a method for finding the volume of an irregularly shaped object. The technique is an extension of finding the area under a curve. We spin the representative rectangle about an axis of revolution, forming a disk that has an infinitely small thickness. In the formula, V is equal to pi r squared dx, r of x represents the function that creates the radii of an infinite number of disks. Dx represents the infinitely small thickness of those disks. The integral symbol represents the summation of all the disks needed to form the solid revolution. Hopefully, when you need to use this formula in the future, you might be able to recall it because you understand it, not because you memorized it.